All right, I want to do a quick video. It's going to be a little bit of a change of pace, but I think it will help you with this week's problem set. So what I'm going to do is I'm going to share my screen and we are going to look at a little bit of R code. Now, I don't expect anyone here to be experts in R or even to use R, but it is a widely used platform for doing statistical analysis, data analysis more broadly, and numerical calculations. And I use it in a lot of my teaching, particularly my graduate courses. And so I'm going to show you a few calculations here that relate. I'm going to show you how I made one of the figures in the lecture slides. And we'll talk a little bit about why this counterintuitive result is the case. So I call this a non-ergodic lottery. Okay, so ergodicity is the property in which the time average of a time series is equal to the state space average. Okay, that sounds kind of abstract. What it means is you have a time series, you have data over time. If you take that average over time, is that average equal to taking an average over the probability distribution of the different states? So the example I showed in class, right, was flipping a coin. Your endowment increases 50% if you get heads, and it decreases by 40% if you get tails, right? And so the state space average, if that's a fair coin, it's 50-50, right, is 150 or 1.5 plus 0.6 divided by 2, right? And it's 10%. So it's 0.1 is the average of that. Okay, so that is the state space average because the two states are up by 50%, down by 40%. Okay, and you may remember from the plot that while that average should go up, in reality, almost all of, in fact, not almost all of them, I did 100, 1,000 replicates, they all basically went to zero within about 200 to 300 coin flips. All right, so clearly the time average, right, which was very negative, was not equal to the state space average, which is very positive. Okay, and that is an indication of non-ergodicity. All right, so this is a non-ergodic lottery. So we're going to set a T-max number of times we're going to flip the coins, 1,000. Your initial endowment is $1. Okay, the number of simulations that we're going to run, the number of replicates we'll go through is 100. And what I'm going to do is I'm going to set up essentially what is, and I just need to think about my code here. Well, N is just a container that is, we give a name to, that we'll eventually put our results into. And then we will do, right, so it's going to end up being a matrix of we're going to stack columns in, these columns that we're going to call temp, right, one after another. So it'll end up being a matrix that will be 1,000 rows and 100 columns. So the 1,000 rounds per replicate and 100 replicates. All right, so that's N, and then temp, so it was the zeros. And what we're going to do is run a for loop. Right? It's a control structure that allows you to go over the length of your two variables, right? The number of replicates and the number of time periods within each replicate. So we're just going to run through those. We're going to reset the first value of our vector that keeps track of this to 1, right, which is our initial endowment for every replicate. And then we basically go through, and this essentially is code to flip a coin. Okay, it's just a sort of fancy R code way to flip a coin. And then we're going to build up this matrix here. And it's not the most efficient way numerically to do it, but it's a pretty small simulation. It'll happen like that, so it doesn't really matter. So I'm going to run this code. Oh, did I? Oh, I didn't put in temp. All right, there we go. Oh, no, I did. All right, well, whatever. It's in there twice. And there we go. So I'm going to generate this T for plotting. And what we will do is we will plot, we'll set up a plot. And what you can see here is, and I made this, sort of trying to be clever here. I made the line very transparent, because a bunch of lines are going to be laid on top of each other. When you lay a lot of like simulation runs on top of each other, you can kind of lose sight of what's going on. So I made these lines, these individual lines, transparent. When you lay a lot of them on top of each other, they'll be less transparent. Okay, and so I use another for loop to just plot the other 99 lines, 2 to 100. All right, and so we can see what that looks like, and they all have that dismal decay. There's this one that looks like it's hanging on, but it isn't really. I mean, it's we can put in a horizontal line. We'll do that at 1, right? That's your initial endowment, right? So you can see that one heroically hung out for like, a little over 650 time intervals. That's the longest I've seen in running this simulation. But it eventually decays down to, a millionth of a dollar. So that's pretty close to zero, I'd say. All right. And we can actually also put in the average line, right? That the average. Well, let's actually look at that. We'll just so you don't have to take it on faith, right? So if it grows by 50%, that means that one of our things is 1.5, right? That's the multiplicative growth rate. 1.5 will give you a growth of 50%, and then it declines by 40% if you get tails. So that means 0.6. That's the multiplier that gives you a 40% decline. You take the average of those two things, and what we get is 0.05. And wow, look at that. That is wrong. That should be 1.05. All right, so it's always good to check your calculations. So we're just going to draw a line in there to show what the prediction should be based on the state space average over time. And it goes in the opposite direction as all the actual simulations go. And so that's that. It's a little counterintuitive. Is there a better measure that we could use? So this is right here, we have this arithmetic mean. Right, and let's actually call it that. Arith mean. All right, arith mean is 1.05. Now, remember that population growth, the growth of an asset, a financial or other sort of asset, is a multiplicative process. Your value, your size at the next time interval at t+1 is equal to your value or your size at time t times a multiplicative growth factor. If that multiplicative growth factor is greater than 1, it will grow. If it's less than 1, it will contract. All right, and notice that the arithmetic mean is additive. We're adding these two growth factors, and then we're dividing by 2 to take their arithmetic mean. But that doesn't capture the process of what population growth is. Population growth is multiplicative. Is there a measure of a type of average that we can use for a multiplicative process? You may have guessed, absolutely, of course there is. And you've maybe even heard of it before. It's called a geometric mean. Okay, so the geometric mean is the product of the two things. So let's do 1.5 times 0.6. Okay, that's the product. And rather than dividing by the number of things that we're taking the product of, we actually take the nth root, right? And since they're 2, it's a square root. So SQRT of that. And look at that. the geometric mean is less than 1, right? And so the geometric mean is going to measure our multiplicative growth rate. And if we wanted to, we could actually put this in here as well. We could do lines t 0.9409, round it, raised to the t. And let's see, color. What color should we make it? Magenta. Send that in. And look at that. Shoots right through the middle of all of our simulations. So the geometric mean is always going to be a better measure of biological or population or financial growth than the arithmetic mean, especially if you have something that is so profoundly non-ergodic as this process is. All right, so I hope that you find that useful. I can tell you that the geometric mean will always be smaller than the arithmetic mean if there's any variance at all. And I don't know if it's worth doing a demonstration of that, but I could. Let's see, anything else? I think that's probably good. So this should help you with one of the questions on the problem set this week. Calculating a geometric mean is not very fancy. You can do it on a calculator. It's pretty straightforward. It's no more difficult really than calculating an arithmetic mean. So think about that. And I hope you find this helpful.